So what does metrology apply to? Well, first of all, there's weights and measures. Pounds, kilograms, cups and liters, feet, inches, and meters. There's also time. How long is a day? Is it one revolution of the Earth? Why is that? Why are there 60 seconds in a minute? Why are there 60 minutes in an hour? Why are there 24 hours in a day? Indeed, why not 12? Or why not 20? In fact, the French proposed that a day be divided into 10 hours to apply the metric system for time after the revolution. So once you agree, by social technology, how to get an accurate and precise measure of things, how do you do so? How do I know that my watch and your watch agree? If we're in the same place and at the same time, this is easy. But if we're not in the same place, what do we do? How do we come to agreement? How do we decide what time it is? How do we decide what a meter is, or a kilometer? Or how do we decide what a pound is? So the problem of metric standardization always works by identifying first a standard, such as a meter, and a unit embodied in that standard for calibrating other phenomena. It could be either produced centrally and distributed, or entrusted to locals to reproduce their own standards. This procedure generated an industry of measuring and instruments to do so. But the standard could be arbitrary. For instance, a meter could be a bar of metal, or it could be naturalized. For instance, it could be a part of the Earth's circumference, or a meter could be the length of a seconds pendulum. The traditional unit, the yard, was a bar that was held in the Parliament and Treasury in Great Britain. It's an artificial unit. But we could also call this bar a meter, or a different distance could be called a meter. So what modern society needed was more standards and more precision. Indeed, a mark of modernity was rationalization of these standards. And commercial enterprise needed it, and international standards needed it. We needed it for standard weights and measures for selling things, and we needed it for selling a new modern commodity, electricity. We also needed to be able to measure electricity carefully such that a new technology, telegraphy, could be implemented. So let's talk about how the international science of precision developed. We'll start with an example. On May 20th, 1875, representatives of 17 nations met in Paris for an international convention of the meter. At the time, every country had a different system for the meter, and indeed, all of their meters did not match up precisely. Upon its initial adoption in 1799, the meter was supposed to be 1/10,000,000th of a quarter of the Earth's circumference. But by 1875, that method had been dropped because it was too difficult to precisely measure the Earth's circumference. Ultimately, what became important was not the size of the Earth, but the international agreement of what a meter was and the replication and distribution of that standard. So after 14 years of metallurgy, the international body had settled on a durable iridium platinum alloy that would be the standard measure of the meter. With this alloy in place, the international collaboration built a machine for reproducing the meter. And that machine used a complicated process for marking off what a meter was and marking off what its subsections were. The procedure worked like this. You would line up on the comparator a standard blank, and then peering through a microscope, the operator would line up 1 meter mark against the standard. For subdivisions of the meter mark, 2 microscopes would be set up, for instance, 10 centimeters apart. Operators would then mark off that length. Sliding the bar down, they would then mark off another 10 centimeter mark, and so on. To make 30 standard meter bars that they did, the operators needed to make 13,000 marks. A single slip on one bar would mean that the entire bar would need to be repolished and started over. So this then was a complicated procedure. So everything was ready in 1889. That was 15 years after they started, and the representatives of each country were ready to take home their respective meters to their own countries. But they also needed to store a master copy of the meter. Why do they need a master copy? Well, what if France's copy, or Britain's copy, or Germany's copy somehow got damaged? How would you know that it had been? You would have to compare it against the master copy. But where do you keep the master copy? Where do you keep an international standard? Ultimately, the agreement was that it would be kept in a safe that could only be opened with a simultaneous use of 3 keys They were to be kept by the leadership of the International Conference and by the director of the French archives. The France would be in France, but it would not be officially in French control. It would be an international archive. It would be something like an embassy or a free trade zone. How about time? How was it standardized, and why? The answer was that time was distributed. It was something like our own smartphones, where time is sent out by a signal over internet connection. In the 19th century, in Paris and Vienna during the late 1870s, industrial steam plants injected subterranean pipes with compressed air and then modulated that pressure to set clocks that were pneumatically connected to it all around the city. But there was a 15-second delay caused by the time it took for the pressure wave to race under the streets of Paris. At first, this was not a problem. Yet time sensitivity had sufficiently mounted by 1881 that even this tiny delay caused by the clocks at different points in the pipe network to differ from one another and from the observatory, that people were worried. The solution was to provide retarding weights on every clock. These would be calibrated so as to account for the different distance of each clock from the central clock. Two striking features of time coordination emerged from this little story. First, time awareness had become acute. Before the 19th century, clocks normally did not even have a minute hand. Now, a 15-second discrepancy could drive engineers to modify public clocks. Second, transmission of time, even of a pressure wave traveling at the speed of sound, looked to professionals and to the public like a problem that needed correction. The answer was developed in 1879, where a dozen synchronized clocks would dot Paris, joined by a telegraphic cable to the mother clock in the Paris Observatory. Built precisely on the model of coordinated precision that they had erected in their own observatory, each of these secondary clocks had its own mechanism to run 15 seconds fast each 24 hours, and a controlling pulse from the observatory drove an electromagnet in each public clock, and that magnet slowed the pendulum, pulling the remote clock into synchrony with the mother clock. Each secondary clock then radiated time electrically, resetting public clocks in city halls, squares, and churches. Still, there were spatial and legal limits past which the observatory time wires would not go. So why did the Victorians care so much about this? Well, one answer was mapping. If you consider that you can measure the distance east to west by time, you have part of the answer. If you were in DC and you have a friend in New York, and each person sets his own clock to noon, when the sun is highest in the sky, they could determine the longitude difference between New York and DC simply by traveling and carrying a clock from one place to the other and measuring the time discrepancy. People tried this again and again to measure the distance from London to Boston, and every time they got different results. Indeed, 12 clocks traveling on a single ship would not agree on the time. So they could not agree on the distance from London to Boston, from London to Paris, from Paris to Berlin, and so on. This was no small thing. This set the boundaries of empire. It set a problem for getting armies to coordinate such that troops could get to the right place at the right time. And aside from the problem of governance, it was also a problem for commerce, specifically for trains. By 1848 and 1849, railroads began to form voluntary associations for time coordination. After November 5, 1849, all trains in New England were to adopt Boston time as given by William Bond and Son Company, number 26 Congress Street. This was not just a matter of money and convenience. Indeed, life and death were at stake. For on August 12, 1853, two trains on the Providence to Worcester line slammed into each other, going around a blind curve. In this accident, 14 people died, and the newspapers blamed the accident on a conductor with a slow watch. So in sum, metrology is a matter of deciding on a measure, such as time, and on a government or an international system for reproducing that system everywhere. That way, once it's done, trains don't collide. That way, the border between Germany and France can be agreed upon. And that way, if I find a new species and report on the size of its parts, anyone around the globe will know precisely what I mean, for their meter stick will be the same as my meter stick.